Hello class, welcome to another math lesson. This time it's module 1, lesson 10. We're still working on scientific notation. This time we're talking about operations with scientific notation. By operations, I mean the 4 basic mathematical operations: add, subtract, multiply, and divide. You will need pages 95 through 101 in your book. Rip out those pages, or if you want, you can keep them in the book. It might also help you to have your notes out from the previous lessons about scientific notation. I will try to summarize them right here. The road so far about scientific notation. Having your notes or your notebook next to you is always a good idea from old lessons, because old lessons help with new lessons. This was the format of scientific notation we've talked about before: a decimal number times 10 raised to the n power. And the 3 rules we had for scientific notation: rule 1, d could be greater than or equal to 1, but d has to be less than 10. So 1 or higher, but less than 10. It means it has to be a single digit in front of the decimal. Number 2, rule 2, this must be multiplication to be scientific notation, because it is a place value thing. And this also has to be a 10. Rule 3, base 10, because that is our place value. Remember, base 10, a 10 with an exponent, is a place value. We talked about that a few lessons ago. So this is scientific notation form. These are our 3 rules. Today, we will use scientific notation to solve math problems, real world problems, using numbers big enough or small enough where we need scientific notation to make our life just a little bit easier. So copy down the notes, pause the video if you have to. But let's show an example before we actually get to the book work. Our example will be, let's say, the world population is about 7 billion, but we'll just say 7 billion because we don't know who just got born and who just died. World population is 7 billion. And that is a fact. It's an estimated, but it's a fact. And another fact is that there are about 4.6 times 10 to the 7th. It's 4.6 times with 7 place values, moving the decimal, 7 place values. Ants for each human. That's a lot of ants per human. That's an odd ratio for us. So if there are 7 billion people and there are 4.6 times 10 to the 7th ants for each person, the question is, how many ants are there? How many ants are on Earth? Well, to solve this, what we should do, we should use a ratio. Now, I know you did ratio math in 6th and 7th grade, so let's use the ratio here. Let's use ratios to help us figure out how to solve this. We know that for every 1 human, there are 4.6 times 10 to the 7th ants. Tells us that in the problem. Each human, 1 human, means that many ants. But we have, on the planet, 7 billion humans. So 1 human means this many ants. 7 billion humans means question mark ants on Earth. We don't know this. This is the unknown that we're trying to find. But these ratios will help us find the unknown because all we have to see how did the numerator in the ratio change, and the same rule has to be followed for the denominator. So for the numerator, 1 human turns into 7 billion humans by multiplying by 7 billion. So the number of ants for 1 human will turn to the number of ants for all humans by following the same rule, multiply by 7 billion. So to find how many ants on the planet, we have to multiply the 4.6 times 10 to the 7th times 7 billion. Now, this is where scientific notation comes in handy. This is why I've been learning it. Because if you don't, you have to do 7 billion looking like that. Kind of annoying to do that. So let's change the 7 billion. First thing we're going to do is make everything scientific notation. I'm just going to put sci not, but you and I both know that means scientific notation. The number of ants for 1 person is already in scientific notation. And 7 billion in scientific notation, I know the decimal has to go here. And to go there means I have to move 9 place values. So this is 7 times 10. I moved 9 place values. Now they're both in scientific notation. And I need to solve this. Now the first thing I notice, let's look at what kind of math I'm doing. You know what kind of math is in the problem. This is all multiplication. Every type of math is multiplication. Multiplication, 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 which means I can do a couple things. I can combine the commutative property when everything is multiplication, and I can use the associative property when everything is multiplication. The commutative property helps me move the numbers, lets me move the numbers around. So I'm going to put the decimals next to each other and the exponents next to each other. And the associative property, when everything is multiplication, lets me choose which parts to do first. So I want to do that part, and I want to do that part. I can choose what order I do it in when everything's multiplication. So now I'm going to multiply what I put in my parentheses. Now this is where I'm okay if you use a calculator. 4.6 times 7 works out to 32.2. And we're multiplying the same base, and so if we go all the way back to our exponent rules, when we multiply the same base, all we have to do is add the exponents, 7 plus 9. So this gives us 32.2 times 10 to the 16th power after we follow the exponent rule. But those of you paying attention and remembering last lesson will notice that, wait a second, this does not follow scientific notation rule number 1. D is bigger than 10. We can't do that. The decimal cannot be here. The decimal has to be here because we have to change from 32 to 3. And so we are moving 1 more place value that way, which means this jump of 1 gets added to that exponent over here. That is how we follow Rule 1. So after we follow Rule 1, we see that there are 3.22 times 10, and now it is not 16 anymore because I moved it 1 more place value. It's 10 to the 17th. And that is how many ants are on the planet Earth. By the way, if you want that in a standard, that is scientific notation form, you want to know how many ants are on Earth. 3.22 is 322. Here's where the decimal used to be. I need to move it 17 places. That means 1 place, 2 place means I need 15 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That, my friends, is how many ants are on Earth. Let's see, hundreds, thousands, millions, billions, trillions, 322 quadrillion ants on the planet Earth. You can write it like that in standard form. That's the answer in scientific notation. I don't know about you, but if I'm writing it, scientific notation looks a lot easier. That's why we use it, and that is an example. So that's our example of how to do scientific notation. Let us try some exercises now. Open up your math book, go to page 95. Your page 95 should look an awful lot like that one. Exercise 1 on page 95, talking about the speed of light. The speed of light is 300 million meters per second. The sun is approximately 1.5 times 10 to the 11th meters from Earth. How many seconds does it take for sunlight to reach the Earth? So what we need to do is we need to take, okay, so light travels that far in 1 second, and Earth is that far away. So light, let's look at our ratio again. Light is 300 million meters in 1 second. And we want to see, okay, how many seconds for 1.5 times 10 to the 11th meters? Question mark, seconds. Well, we need to see, well, this is a little bit hard because we don't know exactly how this multiplies to make that. But what we can do is we can say, okay, 300 million times some number times x makes this. So we know 300 million times x, 300 million times x makes 1.5 times 10 to the 11th. So how do we find what x is? Well, basic algebra, you learned it in 6th grade. To get x by itself, and if this is multiplication, you divide both sides by the coefficient, 300 million. Because 300 million divided by 300 million turns into 1. And then x, and then we divide 300 million on the other side. So that tells us the problem. How much it changes is we have to multiply by x, which is 1.5 times 10 to the 11th divided by 300 million. That's the math problem we have to do to find out how much the seconds change. So we divide these, and that tells us how much the seconds will change. So let's write this problem again. We need to do 1.5 times 10 to the 11th divided by 300 million to find out how long does it take sunlight to reach Earth. Now the first thing I'm going to do is I'm going to put these both in scientific notation to make it easier. 300 million in scientific notation is 3 times 10 to the 8th. I know this because there are 8 place values after the 3 before the decimal. So the first thing I did right here, I changed it to scientific notation, sci-naught. Next thing I do, I'm going to put the like terms together. So I'm going to put the 1.5 and the 3 together, and I'm going to put the exponents together just like that. Next, I'm going to divide both fractions I separated. 1.5 divided by 3 is 0.5. 10 to the 11th over 10 to the 8th, well, that's one of our exponent rules right there. We do 10 to the 11th minus 8. Because the bases are the same, we can just subtract the exponents. Using our exponent rule, we get this as our answer. But that is not in scientific notation. In fact, it's not in scientific notation. It doesn't meet rule number 1. This has to be 1 or more and less than 10. That's a 0. It has to be at least a 1. So let's move the decimal 1 spot to be right there. Now let's look at this real fast. I'm going to write it over here. We have 0.5 times 10 to the third. Now what does this really look like? Times 10 to the third means it gets bigger by 3 place values. So it gets bigger by 3 place values. 1, 2, 3 jumps, and the decimal moves 3 places because there's a 3 right here. Now what I want to do is I want it to be a 5 so that it follows rule 1. But what happens to the exponent here when I move it and make it 5 instead of 0.5? Well, if you look over here, I want the decimal to go here. So I'm giving 1 back. I'm taking 1 back. So it was moving 3, but now I'm doing 3 minus the 1 I gave back. So now it's only moving 1, 2. So it's 10 squared because rule 1 makes me have that be in between 1 and 10. So this has to be a 5, so I move the decimal 1 so the 3 turns into a 2. If you're ever confused about what to change this to, write it out just like I did over here. Now, I also want, so how many seconds does it take light to reach the Earth? 5 times 10 squared. Or if you don't like that, if you want to know exactly how many seconds, remember 10 squared is 100, so it takes 500 seconds for light to get to Earth, which is a little bit more than 8 minutes. So it takes light about 500 seconds or 8 minutes, 20 seconds to get to Earth. About 8 minutes. So if the sun were to blow up right now, we would not even know it for 8 minutes. Cool, that's true. Okay, moving on to exercise 2. Hopefully you get this. Hopefully you know the pattern about how to solve the answer. Remember, it's always about what we start with and how we play with the math rules to get an answer. The math rules I used this time were putting like terms together because it's multiplication. I can pull things apart. Rules about dividing, rules about exponents, and rules about scientific notation to help me find my answer. So part of this is just practicing and using the rules you know. For exercise 2, we're talking about more space stuff because space is an easy place to talk about really big numbers because space is so huge. Let's talk about the moon. The mass of the moon is about 7.3 times 10 to the 22nd kilograms. It would take approximately 26 million moons to equal the mass of the sun. Determine the mass of the sun. So we want to figure out the mass, how much matter is in the sun. So let's start again with a ratio. First, we know that 1 moon is 7.3 times 10 to the 22nd kilograms. We also know that 26 million moons equals 1 sun. So we can use this ratio to solve it because we want to know how many kilograms are in that 1 sun. So this is our unknown right here. So how do we find this? Well, we follow the ratio rules. How did 1 moon turn into 26 million moons? Well, you multiplied by 26 million. Which means we need to take the 1 moon mass This is mass of one moon, and multiply it by 26 million for one sun. So one moon times 26 million moons equals one sun. So one moon's weight times 26 million moons' weight will be one sun's mass. I'm sorry, I said weight, I meant mass. One moon mass times 26 million moon masses equals one sun mass. So this right here is the equation I need to solve. I need to do 7.3 times 10 to the 22nd times 26 million. And already you've guessed that I need them both to be in scientific notation. You know that. I know that. You know it. I know it. The American people know it. Let's do 7.3 times 10 to the 22nd times, remember this has to be following rule 1, 2.6. So the decimal is going to go here. Times for rule number 2. Base 10 for rule number 3. And how many place values do we have? Well, there's 1, 2, 3, 4, 5, 6, 7 place values now after I move the decimal. So there's 7 place values the decimal moved. Next thing I'm going to do, just like before, if you remember the example I did about 5 minutes ago, if you don't, go back and look at the example because we're going to do exactly the same thing. I see that everything is multiplication. When you see everything is multiplication, you have a bunch of properties that you can start using. I'm going to use the commutative property and the associative properties of multiplication because those will really help me get to a place where I can solve this. Remember, the commutative property lets me move things around. So I'm going to put the decimals next to the decimals and the exponents next to the exponents. The commutative property tells me I'm allowed to do that. The associative property tells me that I can make groups wherever I want when everything is multiplication. So that makes it a lot easier now because I know how to combine those. I know how to combine those. I just need to multiply now. I have a plan about how to multiply easier. Again, I'm okay if you use a calculator for this. After you multiply this, it's 18.98. You do not have a calculator at home, you can ask me and I will give you you can come to school and pick up a calculator, or there is an online calculator linked on our Symbaloo page. So use the online calculator if you want to. You know, when we multiply the same bases, we can add the exponents. It's a very popular rule. So let's finish that exponent rule and add the exponents. To get 10 to the 29th, I use the exponent rule. And you're going to find out, again, Mr. Baylor, this is not following rule 1. The decimal needs to be here. We need to move it one place. You are absolutely right. And when we move, we need to make rule 1 true to get 1.898. And when I move the decimal one more place away from where the decimal started, it needs to get one more bigger. So what is the mass of the sun? The mass of the sun, 1.898 times 10 to the 30th kilograms. Hopefully you see how I found my equation using a ratio and the different steps I used to solve my equation. This takes practice. I hope you are practicing. Speaking of practice, exercise 3 has more practice on it. Exercise 3 on page 96. The mass of the Earth is 5.9 times 10 to the 24th kilograms. The mass of Pluto is that number. Compared to Pluto, how much greater is Earth's mass than Pluto's mass? How much greater is not asking how many times greater, it's asking how much greater. Those are key words to know that you should be subtracting. we need to do Earth minus Pluto to find how much greater Earth's mass is. So Earth minus Pluto, they tell us Earth right there. Earth is 5.9 times 10 to the 24th. Minus Pluto, I'm not even going to copy that whole thing. I'm just going to turn it into scientific notation. I know it has to be 1.3 to follow rule 1. I know it has to be multiplication to follow rule 2. I know it needs a base of 10 because I'm talking about place value, and that's rule 3. But how many tens, how many place values did I move? Well, let's check. I like to count by threes. 3, 6, 9, 12, 15, 18, 21, and one more, 22. So I moved the decimal 22 places. So that's the scientific notation. Let us eat. Now you'll notice right here, there's a problem with this. This is not multiplication like the last examples. This is subtraction. So I cannot use the commutative and associative properties. Those only work with multiplication. Can't use them. Subtraction, remember, with subtraction, when we have subtraction, the place values must match. Place values must match. These place values do not match. We have 24 place values, we have 22 place values. Those don't match. So what I need to do, I need to make them match. Like we've done in previous lessons, I'm going to use an exponent rule to make them match. I'm going to do it with the Earth's mass. Because I know the exponent rules, 24, 10 to the 24th, is the same as 10 to the second times 10 to the 22nd. Because I can do 2 plus 22 to make 24. Why did I split it up like this? Because I want this to match this. Now I have 2 10 to the 22nds. Now the place values almost match. I just need to get rid of this 10 squared. Well, what I'm going to do is I'm going to do 5.9 times 10 squared. I'm going to multiply 5.9 times 10 squared. 5.9 times 10 squared means the decimal, it's getting bigger. The 5.9 gets bigger because it's a positive exponent, and it gets bigger by 2 place values. So it gets bigger by jumping 2 place values. So now instead of 5.9 times 10 squared, I have 590. So those two pieces turn into 590. And now the only place values I have left in the equation match. I have matching place values now. Now I can use a property. Because the place values match, because I have the same thing inside both parentheses, I can use the distributive property. Remember the distributive property, if I have the same thing in 2 sets of parentheses, I just pull that out of both of them. So now I have 590 minus 1.3, everything times 10 to the 22nd, because I did the reverse distributive property. Now what I'm going to do is I'm going to subtract what's inside my parentheses. 590 minus 1.3 is 588.7, and the 10 to the 22nd is still there. And you see we're very close to getting a scientific notation answer, except we still need to make it match rule 1. We need the decimal to be here, not here, which means it is moving 2 spaces. 2 more spaces need to go into that exponent. So I get 5.887, and I gave it 2 more spaces, so I get 10 to the 24th. So how much more is Earth's mass? It is 5.887 times 10 to the 24th kilograms. more than Pluto. Fun times. You see how I understood my question? I saw that the words how much greater means subtract. So I set up a subtraction equation. And I used my exponent rules. I used multiplication skills. I used the distributive property. I used subtraction. And I used rule 1 to get a scientific notation answer. Let's try this again using exercise 4. Now this one is saying use the information in exercises 2 and 3 and find the combined mass of the moon plus Earth plus Pluto. So you have to use exercises 2 and 3. In exercise 2, they give us the mass of the moon right there. In exercise 3, they give us the mass of the Earth and the mass of Pluto. So we need to add all these together. The moon mass that we saw in exercise 2 in scientific notation is 7.3 times 10 to the 22nd. Plus the mass of Earth. Oh, by the way, I'm adding because it says the word combined mass, which I know are key words to mean to add. The mass of Earth in exercise 3 is 5.9 times 10 to the 24th. Plus the mass of Pluto, which is this, but I already changed it to scientific notation there. So I'm just going to write the scientific notation that I already did. I do not have to do the same work twice. Now there's this addition problem. Already you can see what you have to do for the first step because we are adding, and up here we said subtracting the place values must match. Well, also when you add, the place values must match. That's why you can't do like $5 plus 5 quarters equals 10 quarter dollars. No, you have to make the place values match. So the first thing you're going to do is you're going to make these 3 place values match. And I want you to do the same thing we did right here. It has to be 10 to the 22nd for all 3 of them. But the good news for you is in exercise 3, we already changed Earth to 10 to the 22nd. So we already did the work here. I'm just asking you to do it again. So take a minute, pause the video, solve this equation, and tell me the combined mass of the moon, Earth, and Pluto. When you unpause the video, you should be ready to check your work with me. Okay, let's check our work. First thing you should have done is use the exponent rule, just like we did in exercise 3, to make all the place values the same. And just like in exercise 3, you should have got that it is this when all the place values are the same. Just there to there is the same as that to that. Now that all the exponent rules are the same, we can use the distributive property. Because everything's the same, let's pass the 10 to the 22nd out of all 3 parentheses. So we get 7.3 plus 590 plus 1.3 with 10 to the 22nd on the outside. Next thing you need to do is add what's inside the parentheses. Hopefully you used a calculator for that to get 598.6 times 10 to the 22nd. And what you should have seen then is that is not in scientific notation. I'm not done yet because I want the decimal to be there to match rule 1. So to match rule 1, this decimal here needs to move 2 more spaces. So we move 2 more spaces. So now we have 5.986 times 10, not to the 22nd anymore because we moved 2 more spaces. Now it's 10 to the 24th. So the combined mass of the moon, Earth, and Pluto is 5.987 times 10 to the 24th. kilograms. Combined mass of all three. Okay, if you need to take a break, pause the video whenever you want, but I am not tired. I'm going to keep on going to exercise 5. Exercise 5. How many combined Moon, Earth, and Pluto masses, which was the answer to exercise 4, how many of these fit in the mass of the Sun, which is the answer to exercise 2? So it's asking, we have the Sun, how many of Moon, Earth, and Pluto fit inside the Sun? How many of these fit inside the Sun? Which, if you look, it's a division problem. So I look at my answer to exercise 2, which is 1.898 times 10 to the 30th, that is the mass of the Sun, divided by the mass of the Moon, the Earth, and Pluto, which is 5.986 times 10 to the 24th. How many of these fit inside of these? How many equal the mass of? It's a division problem. First thing I'm going to do is I'm going to separate my like terms from each other. So I'm going to take the decimals, put them together, and I'm going to take the exponents and put them together. Then I'm going to divide both fractions. I'm going to use a calculator for this one. You get about 0.32. And you know how to do this one. You're just dividing the same base, so you subtract the exponents. So this one, you're going to get, after you subtract the exponents, you get 10 to the 6th, and you use the exponent rule for that. And you see the problem, because this does not match Rule 1. Rule 1 says this cannot be smaller than 1, so we need to move the decimal here. So it moves this way. It's giving a number back. It's getting smaller. So to follow Rule 1, now what's different is the decimal is jumping a different direction. So let me show you. We have 0.32, and it's 6 place values. So we're jumping 6 place values. 1, 2, 3, 4, 5, 6. The new decimal is here after we jump 6 place values. But we are putting the decimal right here. So we had 6 place values, but we took away 1. So these 6, and they gave us 6, and we gave 1 back. So we get 3.2 times 10 to the 5th now. Remember, you can always draw it out like that. So how many moons, Earths, and Plutos fit inside the Sun? 3.2 times 10 to the 5th moons fit inside the Sun. Well, moons, Earths, and Plutos, which is 320,000 Earths, 320,000 moons, 320,000 Plutos, all together will fit inside the Sun. Let's look at the exit ticket. The exit ticket, I'm going to start it out for you, and then I want you to try it on your own. Exit ticket for number 1 says the speed of light is 3 times 10 to the 8th meters per second. The Sun is that many meters from Mars. How many seconds does it take for sunlight to reach Mars? Well, this should sound familiar because we did the exact same thing with how long does it take sunlight to get to Earth. And that question was exercise 1 on page 95. So if you need to know how to do this one, go back and look at exercise 1 on page 95. So try it yourself. If you do it correctly, you should come up with the answer that it takes 770 seconds for sunlight to get to Mars. 770 seconds. So try it yourself, check your work, and look at exercise 1 on page 95 to help you. Now for this one, it says exercise 2 on the exit ticket says, if the sun is approximately 1.5 times 10 to the 11th meters from Earth, what is the approximate distance from the Earth to Mars? So you need to know how far away is Earth from Mars. So let's draw a little diagram. We have the sun, we have Earth, and we have Mars. This is Mars. It's small because it's small. So the sun is 1.5 times 10 to the 11th from the Earth. And in number 1 above us, it tells us that Mars is that number, which is 2.3 times 10 to the 11th away. So we use the information in number 1. So the sun to Mars is that far. The sun to Earth is that far. We want to find this. So you should see how to find this. If we take sun to Mars, if we do Mars to the sun, and we subtract Earth to the sun, we should get the missing piece. This minus this gives us the missing piece. So you should be able to do 2.3 times 10 to the 11th, which is Mars to the sun, minus 1.5 times 10 to the 11th, which is Earth to the sun, to find out how many meters from Earth to Mars. So I'll give you a few minutes to work on this. Try it yourself. It is a subtraction problem. So if you want an example of a subtraction problem we've done together, look at exercise 3 on page 96. Exercise 3 on page 96 is a subtraction problem you can look at that will help you solve this one. So pause the video, try to solve that, and then you can come back and check your answer. Okay, hopefully you paused the video, checked your answer. If you do all the work, just like exercise 3 on page 96, you should get that the distance from Mars to Earth is 8 times 10 to the 10th meters. That should be the answer you got. So if you did not get that, check your work, look at exercise 3 again, and if you're still stuck, reach out and ask me for some help. We'll have a Google Meet, and I will show you exactly what to do. Or if you still need some help and my explanations don't work, or you don't want to talk to me for some reason, you do have the homework helper on page 99 and on page 100 to help you with any other guidance you might need. Well, let's take a look at the problem set on page 101 right now, because there are 3 problems on the problem set that are more practice for these important scientific notation skills. Number 1 says the sun produces this many joules of energy in 1 second, per 1 second. How much energy is produced in a year? And then it tells you a year is that many seconds. So what you have to do is you have to take the joules in 1 second times the seconds in 1 year to find out how many joules are in 1 whole year. So for number 1, you need to take the joules in 1 second, 3.8 times 10 to the 27th. That's how many are in 1 second from the sun, times 3.1 times 10 to the 7th, which is this, how many seconds in a year changed into scientific notation. So I'd like you to try that. You can try it on your own. That is how you do it. It's a multiplication with scientific notation. So if you want some help with multiplying scientific notation, look at exercise 2 on page 95. Number 2 on page 95 will help you with number 1 on the problem set. For number 2, says on average Mercury is this far away from the sun and Neptune is this far away from the sun. What is the difference between Mercury and Neptune's distances? Difference means subtract. So you need to do Neptune minus Mercury to find the difference in their distances from the sun. So for number 2, you're going to do Neptune, which is 4.5 times 10 to the 9th, minus Mercury, which is 57 million. Now, obviously, you're going to have to change Mercury to scientific notation, and this is a subtraction problem. So again, if you need help with a subtraction example, look at exercise 3 on page 96. Number 3 on page 96 will help you. For number 3, it says the mass of the Earth is that. The mass of Venus is that. For part A, it says find their combined mass. Combined is another way to say put together, so you're going to add for part A. You're going to do Earth plus Venus. So for number 3A, you're going to do the Earth, which is 5.9 times 10 to the 24th, plus Venus, which is 4.9 times 10 to the 24th. You're going to add those together. Fortunately for you, they're already in the same place value, and they're already in scientific notation. If you need guidance about how to work when you're adding scientific notations, a good example would be exercise number 4 on page 96 is adding scientific notations. For number 3, part B, it says, if the sun is this many kilograms, how many Venuses and Earth would equal the mass of the sun? Well, to do that, you're going to have to figure out how many Venus and Earth fit inside of the sun. You're going to do the sun divided by Venus and Earth. Now, this is going to be the sun divided by the answer to 3A. The sun they gave you is 1.9 times 10 to the 30th. You have to find 3A by yourself right here. But we did do a problem that is super similar to this one. How many fit inside the suns? And we did that for exercise number 5 on page 96. So it's the same kind of math. So if you need help for number 1, look at number 2 on page 95. If you need help for number 2, look at number 3 on page 96. And if you need help for number 3, look at page number 4 and 5 also on page 96. Have some fun with it. Check your work with my answer. My answer key is linked online, so you can find the answers. You can find them step by step how to do them. You can meet with friends and talk about it. You can schedule a meeting with me. You can watch one of the other lesson videos. But please try your best, and I will see you tomorrow for the next math lesson.